It would be a storage.
Instead of. Like from the. We should.
You enforce it.
No,
you are. Wait, when is March? Okay. Are they two weeks? Why is she leaving Thursday?
Yeah, so you can probably do that. Thing is though, but it's one of them is entirely different. Is that
Either way that happens, right?
Yeah, because that's. But in terms of like environment fit too, I think it would be better if you started. Ready to find out like you.
Yeah.
And like, say something, they like the third, sure, like. It's just more larger. You know, like,
It's not that hard to do.
You probably could have this, plus if you make it think you know, if you do something that way, yeah, like probably too much. So that was when you go to and you can like too much because
Yeah.
you know probably be
So remember, you have to really push out any search.
Oh, yeah.
Yeah.
People would really see references.
Yeah, I want like obviously you have all the. Obviously, because the stuff for hard trade, if you're thinking you're less longer do.
Like you don't.
So I don't want. Well, I know that apartments, mechanisms of thing, they use for the line life, they create very hard. And then line life 3, and very like, well, yeah, but like only maybe we can, so you don't have you don't. It's not only it's in a lot. But you see, like actually, probably, and so they don't realize it's like they charge them. They don't. That's whatever. Like you have a little timer in there, and it only allows one of this one.
The only thing is a little.
The figure. But people don't know how much they did.
Oh, Jackson, that's like, that's not.
No, that's not.
It's just their own. It's a new entire system.
Like, why would you do that? Like, why would you? Build my notes.
That's why I'm not talking about So if you drag that's what I found if you directly sells you like. There's a lot bigger fight.
I'll be a pass.
Get that. I have everything. There's a good thing.
Yeah. Okay, great, thank you.
Okay.
No, I'm fine. My God, please. Please. Writing down that you.
I feel like.
I don't.
Generational.
Like,
So, all your children, if there's like certain cases, there's gonna be more stuff that these can be specific, maybe something to make it, so you can read twice.
Okay, let me go over problem 15 on page 19. I think there's some questions about that one here. So we know that it's asking for radius convergence. We know we have to go through ratio test. So let's just set up using this and we can bring this in later. But let's see what we can do off of that. We know that we're dealing with a limit as n approaches infinity of a sub n plus 1 over x minus 3 to n plus 1. Divided by a sub n x minus 3 Yeah. Okay, so a sub n, I can just replace with this here, but the a sub n plus 1 is going to be a little bit more involved than that. So I'm going to the side, I'm going to have a representation for a sub n plus 1. So that means I'm going to replace every n with n plus 1, right? So this I can replace with this. And the a sub n, I'm just going to leave that alone because I know that that will eventually cancel out. So let me draw what I'm substituting here. So this is going to substitute for this. Everybody okay so far with the substitutions made? Okay, a sub n cancels out. X minus 3 to the n cancels out. We can do limit as n approaches infinity of this expression. We can just take the ratio of the coefficients, which is 2/3. So we have 2/3. X minus 3 is less than 1. So now we're working to this piece right here. Any questions so far? Okay, so now if I just multiply by the reciprocal, I can bring that 2/3 over as 3/2. Drop the absolute value, so it's really x minus 3 is on either side of 3/2 and negative 3/2. Add 3.
This problem's only asking for.
Yeah, it's only asking for, oh, you're right, just for radius. Right, so this is 1.5, good, yeah. So we don't have to go any further, you're right. Okay, let's look at notes for today. This is page 21. So we know that Taylor polynomial is only an approximation because if we can gather a function that we're trying to copy and take their first derivative, second derivative, third derivative, obviously we can keep going and get a better and better approximation. But the idea is that, well, what if we know all the derivatives of all, of the function that we're trying to imitate? If we can push the infinity out, if we push the derivatives out to infinity, then technically we should have the exact duplication of the function in polynomial form. So x has a derivative of all orders at x equals c, then a Taylor series may be formed that is equal to the function for many common functions. So basically, as the nth derivative at c over n factorial times x minus c to the nth. But we talked about how it's easier if we just kind of have a separate form for the first two terms, because it does, I mean, it does follow this form, but it doesn't quite look like it because this is 0 factorial, this is 1 factorial, and it's easier to just say, okay, that's just y-intercept plus the slope times x minus c. We're basically just building your tangent line equation here. And then after that, then it follows the pattern a little bit better. Second derivative at c over 2 factorial times x minus c to the second power. And then next up, third derivative over 3 factorial, x minus c to the third power. And if c is at 0, then it is a Maclaurin series. And we need to know the following series, e to the x, cosine of x, sine of x, and 1 over 1 plus x. These are ones that have easily repeatable patterns. And we're going to build one from scratch first, and then we'll look at the pattern and work towards memorizing those patterns for these common series. Okay. The Taylor series of these functions are exact when we go to infinity. Okay. And we need to be able to memorize them. All right, so let's build the exponential, or let's build the Maclaurin series for e to the x. Again, Maclaurin series, which just means that it's centered at 0. So we'll do for e to the x. Okay. The nice thing for e to the x is that all the derivatives will just be the same function, right? So f is e to the x, f prime is e to the x, f double prime is e to the x. And then if I evaluate at 0 for all of these, they all will produce what? 1, right? F prime of 0 is 1. F of 0 is 1. F double prime of 0 is 1. Okay. Okay, so it's going to keep following this pattern here. So f of 0 is 1 plus, what's the next term?
X.
Yeah, plus x plus, yeah, 1 over 2 factorial times x squared, or basically x squared over 2 factorial plus, what's the next term? X cubed over 3 factorial plus dot, dot, dot. And then the general form that is going to come out of this is basically just x to the n over n factorial. We need to not only memorize the first how the term is built, but we also need to memorize the general term. The general term is going to be really helpful when we talk about the next section. Because sometimes we have to build a general form of the derivative or of the antiderivative, and knowing where we're starting off is going to be really helpful. Okay, so we see this e to the x down here, 1 plus x over 2 factorial, dot, 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 x to the n over n factorial. My interval of convergence is for all real numbers. Okay, let's build the Maclaurin series for sine. Let's find the first few derivatives here. F prime is sine, followed by followed by
Negative cosine.
back to sine. Okay. All right, so let's find each of this Maclaurin series. So these are all at 0 here. So we'll do f of 0. F of 0 is, oh, sorry, 0. F of 1 is, sorry, my bad. F of 0 is, f prime of 0 is 1. F double prime, third derivative at 0. Fourth derivative at 0, 0. Okay, so sine of x equals, first term, y-intercept is 0, plus 1 x plus 0 over 2 factorial x squared minus, yep, plus 0x to the fourth. So what do you notice about the degrees that show up? Only odd degrees will show up. Okay. Okay, so here's a general form, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, this is also shown below under the sign. The idea is that it's an alternating series because there's that change in sign, right? That's cosine becomes negative cosine, and then every term is going to every other degree, every other odd, all the even degrees will drop out. It'll only be odd degrees, but even with the odd degrees, it's going to keep changing, alternating signs. And the 2n plus 1 will ensure that only odd numbers show up. Okay, so if it was, so basically to create an odd number, you get an even number first, and then you add 1 to it, or you subtract 1 from it. So the 2n plus 1 just ensures that we're always getting an odd degree to be received or to show up. And then likewise, if we build cosine, then this is what's going to show up from cosine. I do want to point out a couple of interesting things to kind of help us memorize the sine and cosine. We notice that sine is what? They're only showing odd degrees. And also that's interesting too, because sine is an odd function. Right, if you look at the graph of sine, it's an odd function, meaning that whatever we have on this side is always going to be the opposite on this side. Okay. And cosine is a what? It's an even function. And if we were to look at the cosine graph, right, I mean, it's going to oscillate like this. But if we were taking the cosine graph and if we were to flip it over the y-axis, you're going to get a mirror image on both sides. Okay, so that I think hopefully that will help us remind us that sine is an odd function. So that's why all the degrees are odd. X to the first power, x to the third, x to the fifth, x to the seventh. Cosine is the even function. Now that 1 is sitting there, but 1 is really x to what power? 0. 0 is an even number, right? So it is technically an even degree, 0 degree, second degree, fourth degree, sixth degree. And if you look at the general rule here, looks a lot very similar to sine. It's just that is because we want an even degree, is x to the 2n over 2n factorial instead of 2n plus 1. So you got 2n plus 1 for your odd function, and you got the 2n for your even function. here's another connection that I want to make between the two series to help you see, if it helps, is let me write the sine function here, or the first few terms again. It's just for demonstration purposes here. Okay. What's the calculus relationship between sine and cosine? Cosine is the what? Derivative. So if I found the derivative of these terms, it should take me to the cosine Taylor series, right? So x becomes what? 1. What's the derivative of x cubed over 3 factorial? 3x squared over 3 factorial, which cleans up to be what? Squared over 2 factorial. Next up, derivative power rule. 5x to the 4th over 5 factorial. The 5's cancel out. I'm left with x to the 4th over 4 factorial. Minus x to the 7th, 7x to the 6th over 7 factorial, which reduces to be x to the 6th over 6 factorial. And this is our cosine function. Okay. So just want to kind of give you a couple of ways to connect between sine and cosine, in hopes that it will help you memorize this, right? The idea is that if you have the sine memorized and if you know what the degrees are, you can, if you forget the cosine, you can just take the derivative of the sine and that will take you to the cosine. And then the way I remember e to the x is the fact that e to the x is basically all the terms of sine and cosine put together, just with no negative. So everything is positive. So 1 plus x plus x squared over 2 factorial, x cubed over 3 factorial. So yeah, so sine is odd, cosine is even. E to the x is the simplest looking one, and it has all the terms, doesn't skip over any term, and every term is positive. And then this 1 over 1 plus x, let's see. Yeah, so let's go to the next page. And well, let me just give a preview to this right here. 1 over 1 plus x. This basically is a geometric series. And if we think of this as my a sub 1 over 1 minus r, right? That's the same thing as 1 over 1 minus a negative x. So this is basically my first term, and that's my ratio. So if I keep multiplying by negative x and I can get to my next term, right? So it's basically 1 and then next term times negative x, so minus x times negative x again, so plus x squared times negative x again, minus x cubed plus dot, dot, dot. So we can build this if we just think of it as a geometric series and then put it into the form of 1 minus r, and then just a sub 1 times r. And if I keep multiplying by r, I can get to my next term. And that is kind of what we're going to be exploring with the next example here, page 22. So the function f of x equals 1 minus x is actually a geometric series. We know that a sub 1 over 1 minus r, where absolute value of r is less than 1, is a converging geometric series. So our function of 1 over 1 minus x is really a sub 1. And then we're just multiplying by x every time. So it's a positive x because the minus is outside the ratio. So 1 times x is x times x is x squared. X cubed x fourth dot dot dot. And our a sub 1 times r to the nth. That's our general rule. Okay, so from now on, especially if there's something that we can recognize, whether it's sine, cosine, e to the x, or 1 over 1 plus x, rather than building our Maclaurin series from scratch, we can just build it off of these parent sine, cosine, e to the x that we have, and then just adapt it. Okay, so let me show you what we mean by that. Sine of x squared, okay, we know it's Maclaurin series, so we can build it off of that. Our parent function is really just sine x, right? And let's just review what sine x looks like. Odd, right? Odd degrees. And then it's going to alternate. So sine x squared, if I want to do sine x squared, all I'm going to do is wherever I see the x, I'm going to replace with x squared. So this becomes what? X squared minus x 6. Good. I'm just going to show the previous step there. Plus, let's do 10. Yeah. Okay, and then we're also going to practice writing out the general form as well. We can also adapt this into general form. So let me write the general form for sine of x, and we can kind of build it off of that. So sine is an alternating series. We know our degrees are only showing odd, so it's going to be 2n plus 1. The problem will say how many terms to work on. Yeah, but right now we're just going to do a few. So if this is sine of x, then sine of x squared, in terms of its general form, it's just going to be replacing my x with x squared. Right? Just going to adapt my general form. I'm not going to build it from scratch. So if I take that 2 and distribute it through to 2n plus 1, I'm going to get 4n plus 2. Okay, let's look at number 4. X squared e to the x. X squared is just x squared, but e to the x, we have Maclaurin series for that. So let's see what e to the x looks like, and then see if we can just multiply the x squared through. So e to the x is the cleanest one. It's all positives, doesn't skip any degrees, and it basically includes all the terms from sine and cosine. And it's just x to the n over n factorial. So if I want to do x squared times e to the x, then I can just take x squared and just distribute it through my e to the x series. X squared plus, what's the next term? Mhm. Plus x to the sixth. And then if I were to combine this together, x squared times x to the n, I can just merge it together and make it what, x to the, oh,
Yeah, at the moment.
sorry, 5. Not multiply, I'm adding, yeah. And this becomes what? I can merge it together to be
X to the N plus 2.
good. So it's x to the 2 times x to the n. If I'm multiplying bases, I'm adding exponents, so I can make it x to the 2 or n plus 2 over n factorial. This is my general term. Okay, let's look at some practice problems here. Number 1 says, what is the coefficient of x to the 6th in the Taylor series for the function e to the 2x squared over 2? It doesn't mean that we have to go all the way to the 6th power, because I think that x squared will kind of accelerate that x to the 6th term. But let's build it from our anchor, from our parents, for e to the x, and then we can throw in all the other things that are involved from that exponent. So we know the parent is e to the x, so we'll start there. I can think of it as 2 different stages here. I'm going to replace all my exponents with 2x squared, and then I'll multiply everything through by 2, by 1/2 rather. So if I want to do e to the 2x squared, I'm just going to replace every x with what? Yeah, with 2x squared. So x gets replaced with 2x squared. The x with the second term, with the x squared, will be x 2x squared quantity squared, and it'll be 2x quantity cubed. We don't have to go all the way to x to the 6th, right? Because I think we can reach the 6th degree just by that third term there.
Does it work? Is it possible to work from like the general series and setting it equal?
Oh, you mean building the general series and adapting it, and then yeah, you can do that as well. I prefer this way. I feel like this feels a little bit cleaner, but I think we want to also practice building our general. Well, actually, I don't think it's worth it with this one since it's only asking for the coefficient. So we'll just kind of build what we need to find. Okay, so this is I mean, we can stop here, right? Because we know that this will give us x to the 6th, and whatever the coefficient is, what we're really looking for. So we don't have to go all the way to the 6th degree from the original. We can just stop here. And now we still have to include what? 1/2, right? So I'm going to multiply everything through by 1/2, even though it's really just the last term that I need. So if I were to distribute that 1/2 through, then my first terms would look like this, 1/2 plus x squared plus x to the fourth. If I multiply that 1/2 to that last term, I get 8/12, which is 4/6. This is the term they're asking about. It's asking for the coefficient of x to the 6, and it's 4/6 the order of 2 rows. Okay, can we try number 2? Can we build our Taylor series from what we know from sine? So start with sine, then build sine of 3x, then distribute the x through, and then see if we can find the first 4 terms from there. Okay. Any questions with 2? Okay, let me do one more problem with us, and then we can stop. So let's look at number 3. Number 3 says, what is the Maclaurin series for 1 minus x squared? Write the first 4 non-zero terms. The way that we want to approach this is we don't know what 1 minus x. We don't have a easy series for 1 over 1 minus x squared, but we do have something that we can build this from, right? We do know that 1 over 1 minus x squared is the same thing as 1 over 1 minus x times 1 over 1 minus x. So if I can just find each of these individual series and then just expand out so that I get my first 4 non-zero terms. Well, I know that 1 over 1 minus x is just going to be 1 plus x plus x cubed. I can stop there because my first non-zero terms will just be a constant degree 1, degree 2, and degree 3. Again, my first term is 1, and then my ratio is x, so I'm just multiplying every term by x plus dot, dot, dot. And same thing with this second one, right? 1 plus x squared plus x cubed plus dot, dot, dot. So I'm just going to FOIL or distribute through. I'll distribute the 1 through first. And I'm just going to write down my first few terms here. So 1, I'm going to distribute just this 1 through first. So I get 1 plus x squared plus x cubed. And then I'm going to take the x and distribute the x through to each of these terms there. So I get x, I'm going to line everything up so it'd be easier for me to add. X plus x squared plus x cubed. There's no need for me to go any further because this one would be x to the 4th. That's too high of a term. I only need my first 4 non-zero terms. Next up, I'll move on to x squared distributed through. X squared times 1 is just x squared plus x cubed. I can stop there. And then this term, x cubed, just I should need x cubed times 1 because everything else is too high of a degree. Okay, so for all these Maclaurin series, you're just kind of taking one of the known series that we've established, and then you're just adapting it and adjusting it and making slight changes to it based off of these parent series. Okay, so your homework, pages 22 through 30. And then it includes the AP practice since we're now done with 10.9. All right, come get your phones.
I don't know.